Okay, good afternoon, everyone. Hopefully you can hear me. So today I'm going to talk about cognitive architecture. And this is going to be somewhat more technical than last time. So I want to encourage everyone to interrupt me at any time if you have questions. But so I guess the place to start is what is a cognitive architecture? So basically, a cognitive architecture is a computational model of the mind. And what distinguishes it from other types of models is essentially its scope. So cognitive architectures tend to have a very wide scope or a very wide view of what they include. And they try to include at least all of the major aspects of the mind that are needed to perform a variety of tasks. So that means usually they will include mechanisms for different types of memory, such as long-term memory or working memory. They include some way of doing subgoal. So what this means is using a lower level goal to achieve a higher level one. Like if you want to open a package, then you might have a subgoal of finding some scissors. They'll tend to have mechanisms for just plain old reactive behavior, where it's like a stimulus response kind of thing. Usually they have some kind of simple perceptual and or motor system. And they generally have some types of learning, although it's certainly not you're not going to find a sort of a comprehensive set of learning mechanisms in the typical cognitive architectures that you would see in humans, but you do see some. There is supposed to be sound for the person who's asking about that. Okay, good. So at least one person has sound. It's probably on your end. All right, so cognitive architectures include all these different aspects of mental cognition. But the other important thing to say about cognitive architecture is that a cognitive architecture is really, it's something that has to be programmed, or at least today's cognitive architectures have to be programmed, meaning that if you want to do a new task using one of these cognitive architectures, you have to write code to achieve that. So the architecture itself is sort of like a platform or a virtual machine on which you're building a program that does a task. But at the same time, a cognitive architecture is more than just a programming language, because it's sort of a more opinionated version of a programming language. It has certain ways of writing the code that it will encourage or discourage, and it provides you a bunch of mechanisms that you wouldn't normally have in a typical programming language. Especially, so examples of that would include pattern matching, and also like sort of a variety of ways of maintaining a goal stack. And we're gonna see specifics on that in a few minutes. But just to give you an overview, that's kind of the essence of cognitive architecture. It's got a bunch of commitments about how it wants to model the mind, but it's also not a mind in itself. You still have to program it. So I guess the way that somebody who works on cognitive architecture would probably describe it is that cognitive architecture is meant to model the aspects of the mind that are sort of universal or constant across tasks, whereas it's not intended to model the particular details of our knowledge about how to do a particular task. Those get left to the programmer. At least that's the way it stands today with current cognitive architectures. So, examples of cognitive architectures. There's really two main ones, or two ones that I would say are sort of the most well-developed, the most mature, the most sophisticated. And those are ACTAR and SOAR. And these are both actually quite old. So ACTAR started off, it has its roots in John Anderson's thesis, which was 1973. So that's a 44-year-old project, and it's still being actively developed. In fact, they just redid their website. And SOAR is also quite old, but also still very much used today, very active. John Laird was at the AGI conference last year talking about SOAR and how he thinks it's a good approach to AGI. So these things they have a long history, and they also, but even despite the fact that they're old, they're still being developed. There are a variety of other architectures as well, Lida and Clarion being some examples, but they don't seem to have as much depth of documentation, or they don't seem to have the same kind of level of development behind them. So I'm not gonna talk about those. I'm just gonna emphasize SOAR and ACTAR today, and mainly SOAR, because on the BasicAI website, I've got a summary document that explains an overview of ACTAR. And so if you're interested in ACTAR, you can go there. So I'm going to try to focus a bit more on SOAR today. The next thing is, why do we even care about cognitive architecture? What does it have to do with AGI? I'm going to try to cover that briefly before we dive into the nitty-gritty details. So why is cognitive architecture important, and why aren't we just doing neural networks, which seems to be sort of the popular thing to do in AI today? The basic reason is that a lot of tasks they're just naturally described by some kind of manipulation of symbols. This is certainly the case with things like solving puzzles, which is one of the prime applications that SOAR is really good at. It's true of reading, of writing, of doing math, of programming. All these things really involve some kind of symbol manipulation. And cognitive architectures show us how to do symbol manipulation in a way that's plausible, that basically corresponds at least somewhat to what we know about how the mind works. Neural networks are not so good at that, and so this is why we really have to be looking at cognitive architecture as well. That being said, cognitive architecture is certainly not a solution to AGI. I think it's basically a subset, meaning that AGI eventually will probably have components that look very much like what we see in current cognitive architecture. But it's probably also going to have a bunch of new things that we don't have yet. And I think the creators of cognitive architecture would probably agree with that assessment. So having said that, and this is a good time for questions if anybody has them, what we're going to do now is dive into SOAR and see some more specific examples of what SOAR can do, and even the particular code that you would write to achieve that. What is a symbol? Okay, so that's sort of a deep question, but just as an example, I would say that, let's say we're just we're trying to solve some kind of mathematical problem. Then an example of a symbol would be something like the concept of a set. So if you're trying to make some kind of proof that involves sets, like if A is a subset of B and B is a subset of C, then A is a subset of C. Like that's an example of a proof in math. And if you're trying to get a computer to do that, then it has to have some kind of ability to manipulate the different concepts that are occurring in that theorem. So one of those concepts would be like the concept of a set. And so we could say that like the word set, or the concept behind it, is an example of a symbol. We could also say that something like, when I said the word A, or the letter A, and I used the letter A to represent one of the sets that I was talking about, by using the letter A, I could say that becomes a symbol as well. So A is a symbol representing, in this case, the particular set that I'm talking about. In general, symbols, you can kind of say that they correspond to concepts. So you might also have like the concept of a chair, or the concept of blue, or the concept of walking. All those things, you could call them symbols. And they, all of these things would also occur if you're trying to write a computer program to do like common sense reasoning, or to manipulate knowledge in some way to generate new knowledge, that tends to involve manipulating these concepts. I guess if you're looking for more information about this, the thing to look at is really formal logic. And any textbook on AI will, or at least if it's an overview of AI, will probably have a few chapters on logic. So that's a good place to look to understand what a symbol is. If you're already familiar with logic, then symbols are sort of, they correspond to like predicates or constants that you see in formal logic. So anyway, that's the distinguishing factor of symbols versus like what you see in a neural net is really that symbols discrete objects, whereas in a neural net, we just have kind of a giant vector of numerical activations, and that's sort of the opposite kind of representation. Anyway, let's dive into SOAR. So as I said, SOAR is good at puzzles and games. And we're going to see an example of a puzzle to understand what SOAR can do. So the example that I want to start with is something called the water jug puzzle. And I took this straight out of the tutorial for SOAR. But it's a very popular puzzle, and you've probably seen something like it before. So the puzzle says, if you have two empty jugs, and they are a 5-gallon jug and a 3-gallon jug, and they're totally unmarked, so that if you pour water into the jug, you have no way of telling how much is there. It's not by looking at it, unless you fill it all the way to the top, and then you know it's 5 or 3. And the goal is, assuming you have a supply of water, how can you make it so that you have exactly 1 gallon of water in the 3-gallon jug? I'm going to give you a minute to think about that, and then I'll tell you the solution. So if we just do a little bit of trial and error, it's not too hard to find how to solve this. Basically, you fill the 3-gallon jug, you dump it into the 5-gallon jug, and then you fill the 3-gallon jug one more time, and you pour into the 5-gallon jug until the 5-gallon jug fills up, and then at that point you would have 1 gallon left in the 3-gallon jug. The particular solution is not too important, but that's just, if you were curious, that's how you do it. Okay, so now we can talk about how this SOAR, or how this problem would get translated into SOAR. And to do this, SOAR will generally try to, or what they encourage for modeling problems is to think of problems, or think of puzzles in terms of 3 things: a state, operators, and goal. And so a state represents the current situation that you're in. In our case, that might mean that, like, you have a state where you have both jugs being empty. And we could represent that by saying, by the sort of notation I used here, where it says the 5-gallon jug has 0 and the 3-gallon jug also has 0. Then you have your operators, which are the various actions that you can take that would modify the state. In this particular problem, the actions available to us are, we can either fill a jug, we can empty a jug, or we can pour from one jug to the other. And when we pour, we're going to assume that we continue pouring until either we run out of water or the destination jug fills up. And then finally, we have the goal, which in our case would be to make the 3-gallon jug have 1 gallon of water. So for now, we're going to assume that SOAR solves this task within its own mind, so to speak, rather than kind of taking actions in some kind of external world, which is also possible. SOAR does have mechanisms for that, but it, just for simplicity, will assume that it's solving it in its head. So the next thing to understand is what the state space of SOAR looks like. And in other words, like at any given moment, what is there that is kind of in the memory of SOAR. And I just want to make a side note that that's not the same thing as the state space of the problem. So just keep that in mind. The main part of SOAR's state is what's called its working memory. That's basically where most of the action happens. And as another side note, when SOAR talks about working memory, it's really something that's not quite corresponding to human memory because it has a much greater capacity. But that's not too important for the moment. The structure of working memory in SOAR is basically that it contains a bunch of objects. And these objects, each of them has like a table of keys and values, and then they can also reference each other. So early on in the process of solving the water jug problem, the state of working memory would consist of 3 objects, or at least 3 of them are important. So you can see those here. You've got this S1 object, and it sort of represents the problem as a whole. It's got a name field, and it says that the name of the object is water jug. The purpose of that is just to tell SOAR what problem we're working on, because different problems call for different actions. And then this S1 object that's representing the problem will also make reference to 2 other objects, J1 and J2. Those represent the jugs that are involved, and in turn, the objects representing the jugs will be marked with their volume and their contents. Over time, as we work on the problem, the contents field of the jugs is going to change to represent the changing contents of the jugs. So the way you sort of kick off the things in SOAR is you write a rule that says, basically, SOAR, if you're not doing anything right now, why don't you create these working elements, working memory objects, S1, J1, and J2. And then, so it does that. And then once those are created, SOAR will react to their presence in working memory. And its reaction will kind of invoke the necessary behavior to solve the problem. And so now what we're going to do is we're going to look at what additional rules and code we have to write to make that problem-solving process happen, starting from this initial state. The main process that SOAR goes through to perform action is it's got this cycle of decision making, and it's a 3-step cycle. First, it proposes an operator, and remember, in our case, what an operator is something like fill jug 1 or empty jug 2. So first, it proposes operators, and it may propose several, because often there's several things that you could do. Like you might have the option of if you want to fill jug 1 or fill jug 2. Second, out of all of the operators that are currently proposed, it will pick one. And then third, it will actually apply that operator by doing it. And then the cycle just repeats until you're done. Now, steps 1 and 3 here are handled by rules that we have to write ourselves. And those rules are called production rules, and they have a kind of an if-then structure. So they're saying, like, if this situation holds, then do this. We're going to see those in a second. I'll also point out that Actar has a very similar notion of production rules. And step 2 is done by SOAR itself. So in step 1, we do the work of defining what operators should be proposed when. We also do the work of defining what operators are better than what others. In step 2, SOAR will look at our preferences and look at what's on the table and pick the best one. And then finally, in step 3, SOAR will apply the operator, and again, we have to write the code to do that. In the particular case of the water jug task that we're working on now, we're going to write rules that say that out of the different proposals that we might have at a given time, we don't even care which one's chosen. And so SOAR is basically going to act at random. We're going to clean that up later, but for now, operator selection will be random. So first I'm going to show you how you might apply one of the operators after it's been chosen. So this is the code that's used to apply the fill operator. Once you've decided, or once SOAR has decided in phase 2 that it's going to do a fill operator. Basically, this is a case of pattern matching. And so on the top half of the rule here, you can see these are all things that are conditions. So SOAR will try to see if these conditions hold, and if so, it will do the stuff that's described at the bottom. So to describe the condition that's going on here, basically each piece of the condition corresponds to an object that must exist in SOAR's working memory. So what this is saying is that there has to exist a state that represents a water jug task. There has to exist an operator that is named fill, and there has to exist a jug that the operator refers to. And in addition, the operator has to be actually selected. So this thing here, where in the state there's a field called operator, and it's making reference to an object O. that is something that is added to that working memory element when SOAR makes the selection. So if SOAR makes a selection of a fill operator, then it's going to add into the working memory this field operator pointing to another working memory element that represents the operator. And so the condition here is saying that not only must an operator be chosen, but that operator that has been chosen has to be a fill operator. And then the purpose of the J stuff here is saying that whatever jug has been chosen to be filled, we're going to use the variable volume and contents to represent its volume and contents. So that may have been a little bit confusing if you haven't seen something like it before, but the keyword to look for if you want to learn more about this kind of thing is production rules and/or pattern matching. This is really a case of pattern matching. And the bottom line is that SOAR will detect if we've decided to do a fill operator, and it will bind the variables volume and contents to represent the current volume and contents of the jug that we're going to fill. Then when we do the action of filling, all we do is we modify the contents of that jug so that they are changed to be the volume of the jug. So instead of having an empty jug, now we have a jug whose contents are the entire volume of the jug. The second line at the bottom here just removes the old value of the contents field. Nick points out that this reminds him of Prolog, which is, yeah, that's a good analogy. There's a lot of similarities there. Prolog also involves a very similar type of pattern matching and rule application. So if we were to take this rule and apply it, if this happens to be the operator that gets applied first, then the situation we would end up in is shown here. And there's really only one change in working memory, or at least one significant change. I have suppressed a lot of unnecessary detail. The major change is in red here. The contents of jug 1 have been modified to be 5 instead of 0, which is what would happen if you fill that jug. So this is basically the process that gets used. SOAR would, after it's done this operator, would just continue picking another operator until eventually it gets to a situation where we're in the desired state. And then you would just have one final roll to tell SOAR to stop once it's hit that desired state. This process, as I mentioned, is not efficient because it's just random, and we can do a lot better than a random search. But at least it'll give you the gist of the kind of behavior that SOAR can do and how you would program it. This is a good time for questions if anybody has any. So the next thing I want to talk about is a second type of behavior that we can get SOAR to do, and that's sort of hierarchical control. And a good illustration of this is this game that the people behind SOAR have invented, sort of as like a test bed for SOAR. And in this game, you have tanks, like the different players each control a tank, and the tanks can like wander around this map. And they do different things like shoot at each other, and they have radar so they can detect each other. And there's different resources they can get, like energy and health and whatnot. It's actually a very complicated game. I was surprised at that. So I'm not going to try to describe it in full, but you get the gist of it. It's sort of like I'm not really a gamer, but it's sort of vaguely like StarCraft, where you have resources and you control units, but you only control one unit. So what this has to do with SOAR is that you can use SOAR to write a controller for one of these tanks. Now, in doing that, one of the things that you might want to do is have different modes, so to speak, that the tanks can be in. And so you might want to have a tank or a mode that's like wandering, where the tank just wanders around. But then if you detect another tank, you might want to switch modes and go into an attack mode or a retreat mode. And so within each mode, each mode should persist over a variety of, or over a long number of turns, and kind of control behavior within that period of time. but it should be able to be swapped out for a different mode later. And so now we're going to see how you can implement that kind of behavior in SOAR. So the trick to doing this is that you have operators that correspond to the different modes, like wander or attack or chase or whatever. And those operators, they are going to be proposed and selected. So that's phases 1 and 2, proposal selection. But we're not ever going to write a rule to apply them. And so this is sort of weird, but SOAR makes use of this mechanism where you get an operator to be selected, but you never actually apply it. And so let's just take a look at the code that would propose wandering, just to kind of get a sense of the circumstances under which we would initiate wandering. What this is showing you is basically, so here when you see input link, that's showing you how SOAR can do perception from its environment. So basically you'll have an object that it kind of appears in working memory called the input link. And then you can look into that input link and see what the sensors are currently telling you. So this rule is basically saying that, like, if the sensors are quiet, like there's no sound, there's no incoming radar signal, there's no incoming missile. If everything is quiet, then maybe it's a good time to wander. And so that proposal to wander gets made here. But as I mentioned, we are never going to write a rule that says how to apply wander. And so instead of being applied, what happens is SOAR says, we've hit an impasse because I've selected wandering, but I have no way to apply it. And so what you see here in this middle part of the diagram is sort of a representation of the state that SOAR will find itself in after wander has been selected. So S1 is like the original state object for this problem, which represents just like the goal of playing the game. Within that goal of playing the game, this operator wander is chosen to be applied, but SOAR recognizes that it has no way of doing that. And so when SOAR gets into that situation, what it will do is actually create a new state object in working memory. And that state is called an impasse, and its presence in working memory is able to trigger additional behavior to try to resolve the impasse. So we can write a second rule, which says that if you're at this kind of impasse where you meant to wander, but SOAR hasn't got any way of implementing that operator, what we're going to propose is to take a move action, and move just like moves the tank from one square to the next square. So that's what the second rule here does. It says if you're in the wander mode, then let's move, maybe. So SOAR will select this move operator and apply move. Now, of course, that doesn't resolve the impasse because there's still got no way to apply the wandering. But it has caused the tank to move. And now it's kind of back where it starts, and so it's going to move again and again and again. And so during wandering, what you have is just this move operator selected over and over, which is exactly what you want to create the behavior of wandering. So even though the wander operator never gets applied, all these other moving operators do get applied while wander is sort of sitting there waiting to be applied. And that's the way that it's sort of roundabout, but that's the way that SOAR implements hierarchical behavior. The way you get out of this is that eventually the conditions that led to wander even being proposed will eventually no longer be met, because you'll detect another tank or you'll detect something else with your sensors, then it will no longer seem like a good idea to wander. And when that happens, SOAR actually automatically retracts the selection of the wander operator. So then all the structure that we showed here pretty much just disappears, and then SOAR is ready to move into some other mode. So that is the gist of how you can get this modal or hierarchical behavior in SOAR, and that can be used for this game. I'm going to talk about one final piece, or one final example in SOAR where we look at the details of how SOAR can do something. And then after that, I'm just going to kind of go back up to the big picture, 50,000-foot view. So the final detailed thing we're going to look at is planning. And to do that, we're going to talk about the water jug task again, which I mentioned was not very efficient the way we did it initially. And so now we're going to see how SOAR would do that kind of for real, so to speak. So you may remember that when we talked about the water jug task, I said that the different operators were chosen indifferently, meaning that we wrote the code in such a way that we didn't care what operator applied when. But now we're going to change that and say that we actually want to use the right operator, quote unquote right operator, the best operator at any given time. And on an operational level, what that means is that when we write our proposal rules for the different operators that can be applied, we're no longer going to say that we don't care what operator happens. We're going to remove all those. There's a way to do this in SOAR where you indicate that you don't care what operator gets applied. We're going to remove those don't care markers. And so what happens then is when SOAR tries to select an operator to apply in the water jug task, it's going to see that there's multiple operators that can be applied, and there's no good way of arbitrating between them, at least not yet, because they're all just tied. Each one looks like it's as good as another. So that's another kind of impasse, just like we talked about with the tanks, but this is called a tie impasse. So the problem here is that there's multiple good operators, and we don't know which one to select. And so SOAR in that situation will create a new state object as 2 here, and it just makes a note that impasse, or that state is a case of an impasse because of a tie. So when you get in that impasse situation, that's like a whole new problem. Instead of your problem being to solve the water jugs, now your problem is to decide what operator to use as your first step in the water jug problem. And so you can have rules for how to pursue that subproblem of deciding. And in particular, the rule that's going to be used, or the operator that's going to be used, is what's called what they call evaluate operator. So now we have a new operator that is being used to evaluate the first operator. So for example, O2 might have been an operator that said, let's fill jug 2. And now we have an operator O4, which says, let's evaluate how good operator O2 was, or how good operator O2 would be. I'm not going to go into all the details here because there's a lot of detail, but basically the way that evaluation occurs is there's several steps. It's got a hierarchical control thing going on, just like Wander. And first, we copy the state of the problem from S1 to S3. So basically what we're doing here is just making a copy of the 2 jugs and their sizes so that we can play with it without messing up the original state of the problem. So we make that copy, we apply the operator that's being considered. So now we can kind of see in our mind's eye what the jugs look like now. And then we say, first of all, have we achieved success? Like after applying this operator in this hypothetical, have we gotten to the state that we want? If so, then we would just say that O2, that's a really good idea. We'll mark O2 as being good. And then SOAR would see that the tie impasse has been resolved, and it would go and actually just go ahead and apply O2. If it's not the case that the problem is solved, and of course that's going to be the case most of the time because you can't just solve this problem in one step. So if you're not done yet, then what's going to happen is you kind of find yourself in the same situation where you have to make a second choice, but it's unclear what to use for your second choice. And so you do a recursive descent where you kind of repeat the same thing over and over again. If you're familiar with programming, you'll see that this is going to just leave the stack to grow and grow. The way that SOAR escapes that is they will notice if you've hit the same state twice. So if you've hit a state that was actually also visited somewhere higher on the stack, then that's viewed as failure because you've kind of just gotten back where you started, and that's not a good thing. So what I've described so far would work in the sense that it does not go on forever. and it would solve the problem. And it's a little bit more, it's a little bit smarter than a random search. It's still not terribly efficient though, because basically, because SOAR is only checking the current situation against situations that were higher on the stack, it's not necessarily going to recognize if it gets into a state it's already seen, because it forgets what it's seen as the stack is unrolled. And so it's not really a true depth first search, which is normally the way you would solve this. SOAR does have a mechanism though that can be used to make this a depth first search, and they call it the chunking mechanism. And what's interesting about chunking is that it actually requires no extra work on our part. It's just purely within the SOAR architecture. And the way it works is that if you turn chunking on, it's an option that you can turn on and off. If you turn it on and you hit an impasse, SOAR will actually remember how the impasse was eventually resolved. And it will create a rule that says, next time if you encounter an impasse that's effectively the same, meaning it meets all the same conditions in the relevant ways, then just do whatever you did last time, like do whatever ultimately resolved the impasse without doing all the work that you used to make that decision. So this is a case of what you would call memoization or caching in a normal program. And when you turn this mechanism on, it will basically make the procedure we just described into a depth first search, and then it's pretty efficient. I'll make a couple of comments about this. So first of all, this chunking mechanism is sort of intended in a loose way to model what happens in a person's brain when we compile behavior. So when we first learn how to do something, obviously it's usually slow and we have to think about it a lot. And then over time it gets what's called automatized, meaning that it just becomes automatic. And the chunking mechanism is sort of intended to model that in a loose way. I would also point out that there's a very similar mechanism for this kind of behavioral compilation in ACTAR. So this is something that's definitely an important aspect of cognitive architecture, being able to compile deliberate behavior into some kind of automatic procedure. And then the other thing to say about this planning process in SOAR is that it's actually there's kind of a lot of magic involved just in the manipulations of SOAR state. And SOAR comes pre-packaged with code that's written to help you with that. So there's a lot of code to do a lot of processing here. There's a lot of intricacy to it, but you don't have to write it yourself. Okay, so that ends the kind of the detailed view of SOAR. And now I'm just going to say a few final remarks about other stuff in SOAR that we didn't talk about too much. Here are some of the other components that SOAR has. It's got a couple of forms of memory. It's got semantic memory, episodic memory, and reinforcement learning, which is also in a sort of a kind of learning, a kind of memory, I guess. And semantic memory is in a sense, it's just like a database that's built into SOAR. It doesn't really, semantic memory as implemented in SOAR doesn't really tell us anything about how human cognition works, I think. It's really just like, here's a database and you can use this database if it suits you. And it has queue-based retrieval, which means you can search the database for certain values or certain queues. But you have to write your own code for all this stuff. So if you want to write something to semantic memory or read something to semantic memory, you have to write the code that actually issues that command. They've also got episodic memory, which is also a pretty simple thing. It just, every decision cycle, it will copy the working memory state, and then you can look back at that later. Again, you've got to write the code to look back. Reinforcement learning, if you're going to use reinforcement learning in SOAR, my understanding is that you have to write the code yourself to issue the rewards. And you have to specify what operator you want to apply reward to. SOAR really only does a small piece of the puzzle. SOAR will take the rewards that your code provides, and then it will use those rewards to make decisions in the future about what operator to use. And then finally, there's a spatial visual system, which I won't talk about. But the theme here is sort of like a lot of this stuff really requires you to write a lot of code. These are very generic, general mechanisms, and they don't really take a strong position about how the human mind works or how it should be modeled. It's more like these are just convenience functions for you. Now, I'm not going to spend very much time on Actor at all because we've already because we're running low on time, and because this link at the bottom of this slide will actually give you a reasonable overview of Actar. But just very briefly, Actar is kind of similar to SOAR. It's got a long-term memory, which consists of chunks. The chunks are really a lot like the objects we saw in SOAR's working memory. What SOAR calls working, Actar basically calls long-term. Actar has what's called buffers, which are essentially, that means like what data is being accessed right now, either being accessed through like a visual system or through retrieval from long-term memory or through whatever. And the behavior of Actar is basically, it has productions which match against the data that's currently in the buffers. And then those productions can take actions or create subgoals or manipulate the goal stack in other ways. One interesting feature of Actar is that it does not have that three-phase cycle that SOAR does. There's no like distinction between rules and operators. There's just rules. And if a rule applies, then it gets used. There's no separate decision phase. In terms of like arbitrating between multiple rules, if more than one rule applies at the same time, this is where Actar has kind of something that SOAR does not, which is Actar will maintain records of how useful each production was and how recently each chunk was used and other things like that. And those features will be used to make decisions when there's a conflict. These mechanisms are actually modeled after humans. So as you're probably familiar, in a person, the likelihood of any particular memory being retrieved is related to how recently it was retrieved and also how often it's been used. So Actar actually attempts to maintain that kind of data about the usage of each chunk, and then that can influence the computation. SOAR doesn't have a mechanism like that. And then Actar has some learning mechanisms as well, which I won't really go into. I think the last two things I'm going to talk about are SOAR versus Actar, and then finally I'll talk a little bit about what these architectures do not have. So SOAR versus Actar, the main difference I would say is that Actar really, it comes from a cognitive science perspective. And so it's really got a goal of building models of what people do and of building models that can be validated in the lab, especially with what's called psychometrics, meaning how fast can a human do this task, or how fast can they respond, or how many errors do they make. Actar has really made an attempt to replicate that data. And from an AGI point of view, that's kind of a mixed bag. Like maybe that's a good thing, maybe it's a bad thing. I think it's something of both. It's good in that they're trying to be close to what humans do, and perhaps bad in that if we don't really need to replicate the errors that people make in an AGI, I would say. But the motivation of Actar is not primarily AGI, I would say. I think the Actar people are really also motivated a lot by trying to understand the human brain in particular. They've done a lot of work trying to map up or match the behavior of their system against even things like fMRI data. And also in keeping with this philosophy of trying to adhere to the mind very closely, they've got a lot of constraints in the architecture about what you can and cannot do to try to match what the brain can and can't do. So overall, I would say that SOAR feels somewhat more powerful, but Actar feels somewhat more realistic as a model of the brain. Okay, so now we've talked a lot about all the different things that SOAR can do, and Actar can do similar things. So what don't they do? The main limitations of cognitive architectures are what I've listed below. First and foremost, the limitation that jumps to mind immediately is that you have to do a lot of coding. And obviously for AGI, that's undesirable. We'd like AI that can program itself, that can come up with new production rules, on its own without having to be programmed. And so along the same lines, there's also this issue that in both Actar and SOAR, not only are you deciding all the code, you're also deciding all of the data structures. And so you're inventing like what kind of working memory objects you want to use, you're deciding what the field names are, and so on. So that whole schema should also ideally be acquired automatically. That's what we want from an AGI. But where cognitive architectures have not really touched that yet. Other sort of gaps that kind of go along with that are there's no built-in capacity for language or logic if you want those things. And obviously those are really central in cognition. If you want those things in SOAR or Actar, you've got to code them yourself. So that's sort of like, that just kicks the can down the road and we're back where we started, where the very things that we're trying to model in AGI, cognitive architecture only somewhat helps with those. And there's these architectures do have different learning mechanisms, but they're somewhat limited / unconvincing. And so an example of a type of learning that these architectures cannot do is self-driven learning, where you have a system that sort of follows its own curiosity and uses that to acquire information. So there are some systems out there that have ideas about these different things, like how do you do self-driven learning, how do you do exploration, etc. And the thing about those is that they tend to be very very narrow in scope. They don't have the same kind of broad scope that cognitive architectures do. I use the acronym UTC here. That stands for Unified Theory of Cognition, which is sort of the same as cognitive architecture. But ultimately, I think for AGI, we're going to need a way to pull together both strands, both the cognitive architecture strands and all of this other types of learning. Tommy asked a good question, which is about AlphaGo 0, which requires a lot less programming. And I think so it's absolutely true that these new neural network systems require a lot less programming, but the downside is they're very specific in what they can do. So AlphaGo 0, it only applies to Go. And so that's kind of a huge limitation. So SOAR is intended to apply to all sorts of tasks, and not just one particular task. Right, exactly. So Nick points out that AlphaGo is still very narrow. So yeah, that's kind of the downside of these neural network architectures. And even if you think that the neural network architectures can be applied to a variety of problems, which is kind of the case, because, like, for example, there was the DQN system that could be applied to all the different, or a variety of different Atari games. Well, if you look at that in a little bit closer, you'll see that those Atari games really have a lot in common. All of them, for example, had a state that's totally observable and a state that can be described by just looking at the screen. So there's no hidden state. And they also had very well-defined reward signals. So neural networks can do certain tasks, but they're also very restricted in what they can do. And they don't have the same kind of generality that we see in cognitive architecture. So what we really want is to get kind of the best of all worlds and have the generality of cognitive architectures and the kind of the lack of programming that we have with neural networks, and something that neither of them can do, which is so like in many of these deep learning systems, they require a ton of training data, and would really like to be able to learn from a lot smaller quantities of data. And that's something that the neural networks can't do and the cognitive architectures can't do. So that's a third problem to be addressed. So I think that's just about all I had. In terms of further reading, if you're interested, both Actar and SOAR have a lot of information on their websites. They have very good tutorials, so you can try those out. All the software is freely available. And they both have recent books. So about SOAR, there's a book called The SOAR Cognitive Architecture, and then there's a book on Actar called How Can the Human Mind Occur in the Physical Universe? And then finally, there's that paper on the BasicAI website and the publications section, which will give you an overview of Actar. So that is all I had, and I'm happy to have questions or discussion. So Hitesh makes an interesting point about this, like system 1 and system 2, that Daniel Kahneman refers to in his book. And so that these two systems, level 1 and level 2, one of them is sort of like the automatic instinctive behavior, and one of them is slow, deliberative, thoughtful behavior, basically. And I would say that that's actually a very common idea, and that kind of two-level architecture, that is actually true of both SOAR and ACT-R. They both have those elements. So when you're talking about level 1 behavior, I forget which one was 1 or which was 2, but the kind of quick automatic stuff, that is basically when you have a production rule and it just fires and the operator is chosen and executed. So that's automatic behavior. The more deliberate type of behavior corresponds in SOAR to these impasses that we talked about earlier. So if you have several operators that could be chosen, or you don't know how to apply any of the operators, SOAR will create an impasse, and then you have to think about which operator is the best. So that would correspond to the other level of system 1 and system 2, where you're doing the slower deliberative thinking. And as we saw, it's possible for behavior that starts out as slow and deliberative to be eventually compiled into the fast automatic processing. That was the chunking mechanism. So I would say that SOAR actually is an example of an architecture that applies those ideas, and ACT-R as well. Other questions, comments? OpenCog. All right, so I don't actually know about the third one you mentioned, AERA, but in terms of OpenCog and OpenNARS, my impression of these in general has been that they're not as well documented and they're not as mature as SOAR and ACT-R. In particular for OpenCog, I haven't really seen, like with SOAR, you can go on their tutorial and you see a very clear explanation of these tasks that SOAR can do and how it achieves them. And I haven't really seen that kind of documentation for OpenCog. So it's hard to get a good sense of what exactly it can or can't do and what's new about it. I know Ben Gersel has written, and his collaborators have written some books explaining a bunch of architectural proposals. So they do seem to have a lot of ideas, but I haven't really seen the clear explanation of like where the implementation stands and proof of concept as to how useful those ideas are and what particular tasks. So I guess I would say that it's kind of too soon to tell where those architectures stand. And the main thing that's in the way is just lack of clear documentation or exposition. With OpenNARS, it's a little bit the same story, where I feel like it hasn't been that well described. And also OpenNARS, it seems to have a focus on some very specific types of inference, especially so OpenNARS has this idea of what they call non-axiomatic inference, meaning you can make inferences that, even if they're not strictly speaking logically valid, they're still they still tend to be good things to infer. And they seem to place a lot of emphasis on this particular problem of inferring things, especially about like categorization, that I guess that just feels like it's one particular problem out of a whole lot of problems, and they don't seem to have the kind of broad emphasis that exists within ACT-R and SOAR. So that would be my general take on those things. Other questions or comments? That's a good question. So Mario is asking if the age of SOAR and ACT-R are sort of downsides now, that just because maybe they've become old and sort of haven't kept up with the times. I mean, there's definitely, it's certainly the case that there's a lot of stuff in Actar and SOAR that's just too fundamental to the idea, and you can't really change it without throwing it away and starting over. But I don't necessarily think that's a bad thing, because these fundamental elements really do have to be there in some sense. Like all these architectures, you see there's some kind of production rules, there's something corresponding to chunks, there's some kind of working memory, and there is some kind of notion of subgoaling. All those things are kind of inevitable. You see them in the cognitive architectures, you see them in human thinking, and to some extent you even see them in programming languages. And those probably just have to be there in some sense. So I wouldn't necessarily say that these architectures have sort of ossified. I think they're still alive and being developed. Although at the same time, I would also say that the particular concerns that the Actar community has and the concerns that the SOAR community has are not necessarily the same concerns that people in AGI would have. And so I'm not sure that Actar or SOAR is really evolving in the proper direction that it would need to if we were to head towards AGI. And so from the last slide, you saw some of those things, like we probably need some kind of self-driven learning and exploration, and maybe a built-in capacity for logic and so on. And neither project seems to be working on those things. As far as I can tell, they have sort of other priorities. So you might say that there's sort of their historical roots have led to their current priorities, which are not necessarily the same as AGI. So Valley asks about generalization and how would you measure generalization, and is there a particular set of tasks that we can define and kind of declare that those are the right ones for generalization? I don't have a particularly strong opinion about that. I think you do have to be somewhat careful in that any particular set of tasks, especially any one task, can be solved, or often you can solve it by just throwing enough programming and engineering effort at that one particular task. I mean, in a sense, we've seen this happen. Like, we've seen this happen with Go, we've seen this happen with chess, we've seen this happen with Jeopardy. If you throw enough effort into that one particular task, you can build a pretty good system. In all three cases, we were able to get a superhuman system. But at the same time, as soon as you kind of focus on a particular one task or a small set of tasks, and then try to say that those are a good representative of generality, then you shoot yourself in the foot, because now all the attention moves to those particular tasks, and you're defeating generality. But I think that that's not necessarily to say that it's impossible to find a good set of general tasks, just that it's not necessarily obvious how to do it. I don't particularly think that saying that DQNs can solve a variety of Atari games, I don't think that's a great example of generality, just because those games do have so much in common. Maybe a better direction to head in terms of generality would be something like the AGI tasks that Facebook proposed. And there's also something recently called, I'm going to type it in the chat, but it was the General AI competition, I believe is the name. And I thought that competition did a decent job of defining some tasks that had some generality to them, and weren't just like all variants of the same thing. At the same time, the interesting thing about the General AI competition was that none of the entrants actually managed to solve the tasks. So there's that problem too. Even if you can define a set of tasks that's very general. Oh, challenge, not competition. Thanks. General AI challenge. But so anyway, the thing about that is, even if you can manage to define a set of tasks that feels general, then you may encounter this other problem that your set of tasks is just too hard. And if it's too hard, it may not do a great job of driving research. So that's kind of the That's sort of what's occurred with like the Turing test, for example. So if you set your goal as, let's try to solve the Turing test, obviously that's a great example of measuring generality. If you could pass it, you could say that you've got a very general system. But nobody can pass it, and even if you try to pass it, like even if you set up a competition for who can do the best job at the Turing test, which has been done, you generally just get gibberish as your results. You get the best sort of like wisecracking, gibberish talking chatbot that doesn't actually advance the AI at all. So it can be very hard to find a set of tasks that's general enough to indicate generality, but also specific enough to make progress on. Tommy asks, what cognitive architecture is the best at natural language understanding? The thing about that is none of them are very good. We hardly have any systems that are good at natural language understanding in any kind of deep sense. Like they actually understand what you're talking about. The one that comes to mind is Sherdlu, which is really old. So Sherdlu is from like 1972. It was by a guy named Winograd, and it was able to understand a variety of commands and questions in this very simplified world where it could manipulate blocks. Like if you said like, take the blue block and put it on top of the red block, or how many green blocks are next to the orange block, it could do that kind of thing. And it did have a fairly deep ability to understand what you meant when you spoke, but at the same time it was very restricted in that it could only deal with this one type of world where the only thing that existed were blocks. It's also old. That was from 1972, and there haven't really been any subsequent projects that have tried to replicate or extend it. So I would say language understanding is really quite very hard and something that we haven't made much progress on, unfortunately. Well, if the questions are over, I think that's probably a good place to stop. I will stay around for a few minutes in case anybody wants to chat more, but otherwise, I hope I will see you next time. Next time will probably be in 4 weeks, same time. So thanks for coming, and I hope I'll see you then.